Hey everyone, welcome back to some more calculus. Today we're going to be taking a look at, what is that, 8.1 through 8.5 concepts review. This is a nice one. This is a little bit on integrals and rate. And what I like about this one a lot is that we're looking at a trapezoidal approximation, and we're using that to, approximate an integral and also interpret what those numbers mean. So let's get started on this, and we'll see you in a second. Okay, a quick read through here. We have one of the basic concepts of integral calculus is the integral as a rate of change of a quantity. Can be used to find the net change in a quantity over a period of time. So for example, if f of t is a production rate of an item in units per month, where t is in months, then the integral from 4 to 12 is equal to the number of units produced between t equals 4 months and t equals 12 months. So basically what we're doing is we're just going to not cancel, well, I guess kind of cancel those units of time, provided that those units of time match with the rate. And that'll give us a change in the other part of the unit, the part being accumulated. Number one says that R is the rate at which a tapestry is emerging from a weaver's room. And the values of R over a 1 hour time period are given as follows. So you have this nice table of values. And the thing that I'm looking for now is a rate, because we haven't set any rates yet. And looking at what I see, we've got T is in minutes. That's over here on this side. Over here, T is in minutes. And then the really important part for me, I mean, the minutes are important also, but the part that I'm looking for a lot is this one right here, centimeters per minute. That means if I integrate over a number of minutes, the integral of R is going to give me a total number of centimeters, of this case, in tapestries. So R is the rate at which the tapestry is emerging in centimeters per minute. Then if we integrate R over a number of minutes, T, we'll get the length of a tapestry. So boom, integral from 0 to 60 of RT is going to give me the number or the amount of centimeters produced during that 1 hour. Number two, use a trapezoidal approximation to estimate the length of the tapestry created during that hour. So taking a look, we look at the T's over here, and we notice that they are all in intervals or in changes of 5 minutes. Basically, we're saying that our delta T in this case is going to be 5 minutes. So we're in 5-minute segments. And this is going to give us an opportunity, since all the delta T's are the same, this will give us the opportunity to use a trapezoidal rule. So the first thing you're going to do is, write down the trapezoidal rule. There we go. Notice you have the 1/2 out there in the front, 1/2 delta T. And all of the interior terms you have multiplied by 2. And all the first term and the last term are not multiplied by 2 at all. Okay, now we're going to just substitute all of our numbers into place. This proves to be a really long calculation here, as you notice. I don't know how many terms this is. I think 13 terms in there. That's really long. But not necessarily difficult. I'm very confident that in an actual AP test, you wouldn't have 13 different numbers in here. So after you've done that, you're just going to use your calculator to multiply and sum all that together. There we go. That integral is equal to 842.5. It's actually just approximately equal to 842.5. We use an approximation method, so we're going to be close, but it's not going to be exactly 842. Or at least I'd be very surprised if it's exactly equal to 842.5. Of course, always we're going to write down a summary of what we have just calculated. Here's our summary. Nope, that's not our summary. Here we go, about 842.5 centimeters of tapestry reproduced in that 1 hour time period. Moving over to the next part, we have let R represent the rate at which rainfall in inches per hour, T hours after midnight. Okay, second function F, let that represent the number of inches of rain that fell in the first T hours after midnight. So for example, F of 12 would be the amount of rain that fell in the first 12 hours after midnight. So let the graph of F of T, use a graph to estimate each of the following. Interpret your results by giving the real-world meaning of each. So the first important task is to really understand the scaling of this graph. Let's take a look at that graph a little closer if we can. There we go. The vertical axis is scaled in units of 1 inch, so that's not really a problem. The horizontal axis goes from 0 to 24 with 1, 2, 3, 4, looks like 6 different intervals in between. 24 divided by 6, and you get that each of those intervals are set at 4 hours. So the first line is 4, second line is 8, third line is 12, etc., etc. R of T is given as rate of rain as the rate of rainfall in inches per hour. So if we integrate R from 0 to 24, what we get effectively is the amount of rainfall over those 24 hours. So how much rainfall is in those 24 hours? Well, F of T gives us the number of inches of rainfall T hours after midnight. So the integral of R from 0 to 24 is the same thing as F of 24, which is about 4.6. I should point that out on the graph. You can see F of 24 here, a little bit up above 4.5, so about 4.6. Next, we get an integral from 4 to 12. So this one's similar to the one that we were just looking at, except for now we're looking at the amount of rain that fell between the hours of 4 and 12. So that's about 4 a.m. and 12 noon. According to the graph, at 12 noon, right over here, what does that look like? That looks like about 2.3 inches of rain since midnight. At 4 a.m., which would be that first line, that right there, that looks like about, 1.2 inches. So if I subtract that, 2.3 minus, 1.2 inches, and that's about 1.2 inches of rain that fell between 4 a.m. and 12 p.m. There we go. A total of about 1.2 inches of rain fell between the hours of 4 a.m. and 12 p.m. 2c. Just to drive that point home even further, we've got integral of r as t goes from 8 to 20. Just like before, we're going to have to, we have this as the amount of rain that fell, except now we're looking at between t equals 8 and t equals 20. So let's estimate that. At t equals 20, which would be this fifth line, at t equals 20, you can estimate that at about 3.9 inches of rain that fell since midnight. At t equals 8, this second line right here, at t equals 8, it looks like about 1.4 inches of rain fell since midnight. So a total of 3.9 minus 4.9 inches, or just about 2.5 inches of rain, fell between 8 a.m. and 8 p.m. There we go. A total of about 3.9 minus 1.4, or 2.5 inches. Probably that is a bit much. A total of about 2.5 inches of rain fell between 8 a.m. and 8 p.m. Let's see what we have for number 3. From the beginning of 2000 to the beginning of 2010, a certain company earned revenues at a rate of R equals T cubed minus 15T squared plus 70T plus $150,000 per year. So we're in rates of $1,000 per year. Where T is the number of years since the beginning of 2000, find the total revenues in this 10-year period. So our first clue that tells me what to do is going to be the fact that the rate here is in thousands of dollars per year. So if I integrate in terms of years, that should give me a total number of thousands of dollars. So if I integrate from 0 to 10, that's going to give me the thousands of dollars in revenues from about 2000 to 2010, which is what we want. So our first step here, let's just set up that integral. We want to integrate r from 0 to 10, and that gives us the integral of t cubed minus 15t squared plus 70t plus 150. Do a little bit of integration. And then now we have something that we can evaluate with our calculator. I notice that the lower limit is 0, so if I substitute 0 here, since it's just a polynomial, I should get a 0, so all I really need to do is substitute that 10, although you want to really make sure about that before you decide to ignore that last term. So let's remember that we're in thousands of, the units here is in thousands of dollars, so we need to multiply by 1,000 to get our actual answer. So the total revenues in that 10-year period is $2,500,000. Again, we're in units of thousands of dollars. I outlined that at the beginning. So our actual answer in terms of number of dollars is $2,500,000. Now we get everyone's favorite connections to calculus, which would be physics. I think I'm a little bit old school in the fact that if the calculus isn't particularly useful, I'm not really worried about that. But that's pretty peculiar to me and most people who are more math-centered than application-centered. So we have many rates of quantities many rates involve quantities other than time. For example, one might regard force as a rate of work done per unit of distance. In this context, the work formula W is going to be an integral from A to B of f of x dx, which can be regarded as another example of a rate being integrated for a net change of time. So, not to complain about this too much, but they don't really give us a whole lot of idea about units or anything, or how those units are going to work. So this seems kind of written, well, I don't know who would have written this. Not particularly interesting, or not interesting, but it's not particularly helpful. And me not being a physics person per se, I'm not going to really be able to give you answers to that as far as units of force, which I'm sure we'll say something like newtons or something, and units of work, which, to be honest, still mystifies me as a math person. So, with question 4, we've got a tub weighing 20 pounds lifted from the ground to a height of 40 feet. As the tub is being lifted, it is also being filled with pebbles, as you do, of course. So that the weight in pounds of the bucket when it is a height x feet is given by 20 plus 30x, or plus 3x. Find the amount of work being done in lifting the bucket and the pebbles. So I think one obstacle here, especially for me, is the realization that what I think of weight, 20 pounds plus 3x, is an expression of force. This is force. 20 plus 3x is my force equation. So if I want to utilize the formula, which is, I'm convinced, everything that I did when I was in high school and I had physics, I just followed the formulas. What I'm really doing is trying to figure out where does the equation fit here. And as we stated before, since that equation or that expression is a expression of force, I can just substitute that expression right into this formula. So I have my work being equal to the integral from 0 to 40 of 20 plus 3x. Now this problem becomes really easy because I know how to integrate, and I can almost ignore, at least for the time being, ignore all of that context. And that gives me this really nice antiderivative, which you can easily substitute or use your calculator to substitute, and you get 3,200. Oops. Got a couple of different oopsies today. So 3,200, I always would like you to write some kind of summary statement here. So what is our summary? 3,200 pound-foot of work is needed to raise that tub those 40 feet as required in the problem. So that's it for us today, and I'll see you next time when we do more calculus concepts review. See you later, everyone.